Hello everybody! I hope everybody's having a wonderful day. So we're going to pick up where we were leaving off last time here. And I'm going to start talking about decision problems. So there's going to be two main kinds of problems we're going to talk about in this class. Decision problems, and the latter being the one that we're going to primarily focus on, optimization problems. However, from a theoretic standpoint, it's very important that you're aware of decision problems and how we can use them. Because they oftentimes tie in for how we can approach optimization problems, or you can look at optimization problems as a generalization of a decision problem. Many problems in computer science are typically formulated as types of decision problems, or at least can be reduced to decision problems. So you can think of a decision problem as one that's typically posed as a question. So I can ask you, oh, is it rainy outside? Is my tie red? Is it green? These are all questions, right? All of them have yes, no answers, at least in the framing that we're going to go with. We're not going to be keeping too many things in the gray here. So I'm going to expect, I throw out a question to you, I expect a yes or no answer. So more formally, if I give you a decision problem pi, every one of the instances, I'm going to call it x again. Every instance x in pi, there's going to be a solution, and it's either going to be yes or no. That simple. Now, I should remark that if you're familiar with, say, the more Turing machine language-specific way of interpreting a decision problem, you can also think of these as where the problem instances, we basically discard all the instances that are no answers, and we only keep the yes answers, where you could describe the instances as those encodings I talked about last day, the binary strings for which they encode each one of our input instances. This can be declared as what is so-called a language in terms of formal language theory. I'm not going to be talking about in terms of that convention here. Instead, I'm just going to assume our problem instances either a yes or no, and I'm not going to kind of delineate between any kind of thing where I'm going to pick a convention. Because I have to mention that because traditionally, decision problems typically are defined where the answer is usually yes. So I'm not going to go too much detail why that is, because this is not an automata theory course. However, for your own interest, you may want to check into that if you find this kind of interesting. So if every one of the instances has either a yes or no answer, imagine my picture I had from last day. You can think of it like this. So each one of these instances, I get some question, which is going to be how I'm going to describe all of these. Each one of these could have a yes answer or no answer. So I give you some input instance, just like in my picture last day, and the solution is just going to be yes or no. Very simple. So for example, this problem instance might have a yes answer. This one might have a no answer. But the point I'm getting at is that every one of them has either a yes or no answer. That means you have the ability to partition all the instances such that so you have either instances that have answers yes or answers no. This realization is very important for later on when we start talking about hardness of approximation. So what I mean by this is that, okay, there's only two possibilities for the solutions, either yes or no. You can take any one of these instances and put it into one of these two buckets, either the yes ones or the no ones. So just keep that in mind. It's going to be rather important observation that we're going to use later on in this course. So what are we going to talk about here? So I want to give you some examples of decision problems and how we might talk about them with respect to the things I talked about last day. Okay. So I'm going to present three examples. So the first example is probably one you may have encountered in the past, is the minimum spanning tree problem. So I'm going to give you some examples here. So the first one, I'm just going to call it minimum spanning tree. Now, just to be clear, the minimum spanning tree problem is an optimization problem. So we need to be a bit more particular. I'm just going to refer to this as the decision variant. So the decision variant of the minimum spanning tree problem. So I'll just to make it a little easier for you to delineate between them, I'm going to call this one decision MST, where MST stands for minimum spanning tree. So what is this problem? So I am given a, now to avoid having to say this many times over and over again, I'm going to assume the graphs, unless otherwise stated, are simple. That means that if I give you a graph, that graph or network, the graph will not contain multiple edges, so it will not contain parallel edges like this. Like if I give you a graph that looks like this is impossible in a simple graph. Instead, it would have to have a single edge like this. So there's no multi-edges or parallel edges and no self-loops. So any business that looks like this, where I have just a loop. So unless I say that it is a so-called multi-graph which has these properties, just assume simple. It's a simple graph. So given a connected, weighted, that means I'm going to have numbers on the edges in my graph. These are going to be associated with costs and weighted, and I have to still add it over as undirected graph. G would be like this, where G is the graph's name, these are the set of vertices, these are the set of edges. And remember, this is undirected. That means that if I give an edge in the graph, you should not assume an orientation on the edges. I'll give an example in a moment. So this is so you might be familiar with this setup where I just say, okay, well now, find me a spanning tree that is a tree, that is a subgraph in my input graph, such that I try to find a spanning tree, which means that it contains all the vertices of the graph, but it's a tree. Such that I add up all of the edge costs or the weights on the edges, and I want to find the spanning tree that has the least cost. Now, in a decision variant, what you normally want to do is you want to pose the question in the direction for which you're minimizing or maximizing. So, in this case, this is a minimization problem. Remember, I'll talk about optimization in a little bit. But I'm sure this problem you're familiar with it or you've run into something like this before. So I'm going to say, is there a minimum spanning tree whose total cost is at most k? So you can pose this as a question. Given a connected, weighted, undirected graph, that's a mouthful, G equals VE, is there a minimum spanning tree whose total cost is at most k? So you'll notice that I've introduced another parameter that for which, if you normally are familiar with this problem, isn't normally there. This is the part that makes this sort of it's more about a decision. It's either a minimum spanning tree with such a cost exists or it does not. So it's a yes or no. So, just to give you an idea of what exactly I'm talking about. So imagine I give you a graph that looks like this. Imagine I have a graph and say the edge weights. Let's take it like this. Note I didn't put this one in the notes, but here's an input graph. It is simple, and it is weighted, and it's undirected. So I haven't labeled the vertices in this graph. However, you'll notice they're weighted. So in this case, it's quite clear what the minimum spanning tree is. So remember, spanning tree is a subgraph for which it contains all the vertices in this graph. So there's 5 vertices, such that I find one of these trees. So remember, a tree is a graph without any cycles in it. It's acyclic. It has no graph. It has no cycles in it. I was about to say no graphs in it. That just doesn't make any sense. So here we go. So this is actually not too hard. If you look at this very carefully, you can see, okay, I have one here, one there, one here, one here. Well, the total cost, if I add up these edges here, you'll see, okay, 1, 2, 3, 4, right? So you notice that if I select this, the total cost of this spanning tree, so the one that I've selected here, is going to be 1, 2, 3, 4. 4, right? Nice and easy. So if I pose this as a question, if I gave you that as the input instance, and I told you, okay, is there one with the total cost is at most 5? You would answer yes, because the total cost, there does exist a minimum spanning tree whose total cost is 4, right? Likewise, if you were to say, instead of this being 5, you make this 4, you'd still say yes, because look, there it is. How about when it's 3? You would say no, right? So now you might naturally ask, okay, well, how do you know that the answer is no? Well, it's because I have an efficient algorithm where I can compute the minimum spanning tree, right? So that means I can actually construct the minimum spanning tree, and I can just simply check what the optimum value of the total cost should be. So in those cases, you can actually say, hey, look, definitively there's no way you can get such a thing out of this. So this is clear for everybody? So just to be clear, so an input instance here, would be the graph G equals B. The weights W. So this is just the weight function. So I give it an edge or 2 endpoints, and it pumps out the number that is the edge weight. And then, of course, I have integer k. So that's what the input instance would look like for this problem. So when you talk about input size, what you do is you compute, okay, well, how much space do I need to record this? Well, if we're only caring about the numbers, or in terms of the size, the number of vertices and the number of edges. Remember, I said last day, you can almost get away for free of assuming that these are of constant size. Now, in particular, in problems that don't involve numbers, you can even get even better than that, because when you label these vertices and edges, each one has a distinct label. So I say, okay, this is vertex 1, this is vertex 2, vertex 3, vertex 4. They don't have to necessarily have any arbitrary label on them. So I can encode them in any particular way that makes it convenient. But however, it's worth noting that a convenient way of measuring the input size here would just simply be in the number of edges and vertices, right? And this is what you would normally do, right? Sorry, input size. So the input size here, it would be fair to consider as the input size big O of the number of vertices plus the number of edges. So this would be a reasonable consideration for the input size. So remember, all these are just kind of labels, and they're all going to take a logarithmic number of bits. But remember, I'm going to assume that you're able to fit these numbers into a word. And likewise, we don't have to get any particular with this, because our algorithms only do comparisons with the numbers. They don't actually, the numbers themselves don't pop up in the running time. It's also worth noting, just on the sake of this, that when I consider algorithms like the one that you would actually use to solve this problem, such as an algorithm like Prim's algorithm, you'll notice that I don't create a giant lookup table. One thing that's worth noting, when we're working with the RAM model, normally it's assumed that a memory access will take at least constant time. So it's going to take, you can assume, just simply for the sake of simplicity, just one step. So like a fundamental operation or a basic operation or a primitive operation, that includes a memory access. So that's why, for example, this is just an aside. You can't just create a giant lookup table and just give you the answer out of that. Those memory accesses for building the table will require a lot more space, and hence each one of those space allocations is a step. But that's just me off the side rambling. That has nothing to do with the minimum spanning tree problem, but I always feel like cramming little details in here because this is kind of like a review. Hopefully that's okay. But the point I'm getting at is that you'll notice that the input size grows with respect to the graph. So the graph itself, and these are just logarithmic measures, right? If I were to actually calculate the time complexity, all these log measures, they're going to still spit out something that's polynomial for me, unless the running time of my algorithm start throwing the numbers into the total running time of the algorithm, which is going to be a bit of a pain in the neck. Like I said, we're not going to worry about that. We'll only worry about it when the problem merits that, okay? Hopefully that's clear. So I'm hoping that I'm not confusing you involving this input size business. So just remember, just think about it in terms of the number of items that you're encoding, because each one of them you're going to just assume, okay, they're just like a fixed number of bits I'm using to represent them, some constant. Okay? Okay, so naturally, the algorithm you want to use here to solve this problem, if I give you any k, any graph, and any arbitrary set of weights, the algorithm you naturally want to use, this is one you can do. You can just run Prim's algorithm. You run Prim's algorithm. And you can just answer yes. Yes, if the, I'm going to go to the next word, if the minimum spanning tree produced has total cost at most. Guess what it is? It's k. It's k. Otherwise, so if you check the total cost of your tree and you say, okay, well now it's actually not that. Instead, it is something that's smaller than that I can totally get. Otherwise, you're just going to simply say, otherwise, no, right? It's worth noting that if you might know the classic implementation of this with a priority queue, well, Prim's algorithm, that is. So this can be done in big O cardinality of E log the cardinality of V. So that one's the classic where you use a priority queue, and then you're just going to greedily select the next closest vertex in so-called, like you think of like a cloud where you're growing a tree, but that's aside the point. The point is that there's a nice efficient algorithm there. Okay, so that's one example. So notice the input size isn't terribly interesting here. So remember, just think of the number of items, not the numbers themselves, because in our machine model, this should be okay. Okay, so here's another problem. We'll call it primes. The primes, given a positive integer n, given a positive integer n is n prime. So recall that a prime number is one for which it has two divisors. One, n itself. In our case, if n was prime, it would be its two divisors would be 1 and n. So this one's a nice number theoretic type problem. So if I give you, say, the number, let's go for an example here. If I give you the number 7, you would of course say yes, that's a prime number because it has it's not composite, correct? That's kind of circular reasoning, but I don't think I need to justify that at this level. It's pretty simple. The number 3, of course, that's it. That's a prime number. How about the number 4? Is 4 a prime number? No, it's a composite number. It's 2 times 2. So my decision problem has to be where I get a positive integer, and I have to decide if the number is prime or not. So if it's prime, I say yes. If it is not, then I say no. You might take a bit of a hint because I keep rambling every once in a while about input size. This is sort of the hint of the lecture, is that this one's a little bit different than the other examples. Because this is a number theoretic problem. It's a problem involving numbers. So, what's an input instance look like here? So an input instance would just be an integer n. Just an integer n, very simple. Now, how about the input size? Let's talk about the input size. What's the input size here? Now remember, we got to go back to our definition of input size. Now, normally I would take the number of items, and then I would just say, okay, well, it's based on the number of items, and I kind of take a look at it like, okay, well, if I apply that same kind of reasoning here, I have a single integer. You're naturally compelled to write, okay, must be constant, right? This is just one number. However, this involves numbers, so we have to be a bit more particular and accurate, and we have to be a bit more accurate in how we measure the input size. So in the cases like when we sort an array, or when we're looking at the graphs that we've been doing, you can get away with inaccurate measures of the input size. You can really drill down and start really writing it down if you wanted to, but you won't find it very particular or productive. You'll just get very similar results. But you have to be very careful about this because every single problem you should treat as a different animal when we talk about the input size. Sometimes it makes sense to use the input size that's a lot more accurate other times. What would I do here? Well, let's appeal to our definition of input size. It is the number of characters for which I use to represent the input. Okay, what is that in here? Well, okay, it's an integer. Okay, well, I know if I give you integer n, I can use big O of log n bits to represent that number. I could get more exact if I want to, but you'll find that I'll typically go to big O or big theta if I want to get more specific in these cases. So, keeping that in mind, I want to point out how you'd solve this problem. Now, naturally, there's all sorts of different algorithms that exist for testing primality. This is really just testing if a number is prime or not. But you might naturally ask, okay, well, how can I do this really fast? Well, there is actually, under our definition of efficient, there is an efficient algorithm for doing this. It is the following one. It's the AKS primality test. This is actually not that ancient either. A lot of number theoretic algorithms can be quite old. This one's a quite more recent development. And there's a lot of algorithms like this still pop up quite recently every once in a while. Now, I should point out that this algorithm takes big O of log n, where all of the log n is together, and I'm going to raise that to the power of 6. I need that word timing. Okay. So notice it takes big O of log n raised to the 6. So this, technically, the way it looks kind of strange, but I have to ask you a question. Is this a polynomial time algorithm? Well, what's the input size? Well, it's this, right? So just to make it a little easier for you to see, if I were to call this like y, for example, let's say that's y. I'm just going to define this to be y. That's just me saying define as in reverse. So I'm just going to say y is that. Well, if I just put y right here, notice it's just saying y to the 6th. Well, this should look rather familiar to you, right? So this is in fact a polynomial time algorithm for primality testing. So this is actually a really fascinating and celebrated result in terms of some of these tougher problems. Because for quite some time before, it was a little unclear if there were efficient algorithms for primality testing just like this one. A lot of them involve sieving methods or other things like that, which can be pretty effective when it comes to large numbers, but that's just aside from the point. The point is that there exists a polynomial time algorithm here. You're going to find in this course, we're not going to be so concerned about how efficient the algorithm is. We're just going to care if it takes polynomial time. So let's do one more example. The traveling salesman problem. So the final example is going to be the traveling salesman problem. So it works like this. So I'm going to be given, remember, I'm just going to assume it's still a simple graph, given a weighted complete graph. G equal to E, like I had for MST. Is there a TSP tour? Is there a TSP tour of cost at most K? So you might know of this problem. Now it's worth noting before I get to anything too crazy here, is that because just in case a complete graph on, say, some number of vertices is where every vertex is adjacent to every other vertex. So I'm going to formulate it in this way just for the purposes of this lecture to make it a little easier to prove a couple things. So imagine I give you a graph. I'm just going to keep it simple, just have 5 vertices. I'm going to assume that every vertex is adjacent to every other vertex. Oh wait, I already have an edge there. I get a little ahead of myself. That one. There we go. I shouldn't try to summon anything with this symbol. Anyway, so all of these have edge weights on them. Now, you might ask, Dan, does this restrict anything? Well, naturally, you can make these weights as big as you want them to be. So just for my purposes, I'm just going to make it so that, just for the sake of time, I'm going to make all the outer perimeter a 1, and I'm going to make all the other edges worth 10. So 10, 10. I think I got all the edges. 1, 2, I got 1, 2, 3, 4, 5. Okay, I got them all. I think I got them all. Either way, what we're going to be doing is we need to find a TSP tour. So a TSP tour is a fun name to describe what is called, so a TSP tour, just for the sake of those that are so graph theoretically inclined, a TSP tour is a Hamiltonian cycle. So that means that it is a cycle that contains all vertices, no repeats on vertices or edges. So it is a cycle that contains all vertices with no repeats on the vertices or the edges, such that, as the name suggests, it's a cycle, so it returns back where it started. So don't worry too much about this, because technically this is redundant. But just because I like to be a little bit intuitive with you, I wrote it down anyways. So I want to find a cycle that passes through all the vertices but with no repeats. So a Hamiltonian cycle, for example, could consist of me going around the outer perimeter. Notice it goes all the way, it goes through every vertex. There's no repeats on the edges, nor are they on the vertices. So I don't go backwards onto another edge or another vertex. Now, the outer perimeter happens to also be the one with the cheapest TSP tor, is this outer perimeter here. So in fact, if you're looking for the optimal solution, if you're thinking about this as an optimization problem, the answer would be 5. So an optimal TSP tor it's 5, right? 1, 2, 3, 4, 5. Okay. So if you were to ask questions about this, as I stumbled, if you were to ask if k was, say, 5, you would answer yes. If it was 4, you would say no, because there is no such TSP tor in this graph. Now you might naturally ask, oh, how do I know that? Well, you'd have to try all possible TSP tors, which requires me to check. Well, there's actually a couple ways you can go about this. I shouldn't say you require anything. I shouldn't get too ahead of myself. That's normally something you should avoid doing, getting too ahead of yourself and assuming that something can't be done. Because I'm going to elaborate. So an input instance here is just a graph G, E. Again, you have the weights W and the integer K. So, what's the input size? So it's going to be the same as we had last time. We're going to be a little bit inaccurate here. That's fine because we're not really going to use the numbers in terms of our running time. Now, I'll explain how this could change how you decide what the input size is in a moment. So I'll just use the same input size as I used before, because we just used comparisons on the edge weights. It doesn't really change a whole lot. So this assumption is appropriate. So there's an algorithm for this. So there is a dynamic programming algorithm actually for this problem. You can just use called the Held-Karp algorithm. And naturally you can just say if the optimal TSP tor is at most k, you're just going to return yes. Return yes. Otherwise, return no. It's worth noting with this algorithm takes exponential time. This one in particular, it takes big O of 2 to the power of the number of vertices in the graph times the number of vertices in the graph squared. So this is an exponential time algorithm. So this is what we would call an exponential time algorithm. Apologize for my writing. This is an exponential time algorithm. So ones for which there's the form at least of 2 to the power of n, where n is part of the input. So this one's a little bit different. Now, I just want to mention just briefly why I said, okay, well, you have to be particular with the input size, because you can actually really think about this. Imagine if I gave you an efficient algorithm for, say, TSP here, the traveling salesman problem. What you could do is you could just keep repeatedly asking questions about the size of the TSP tor. So what you could do is you could just start at, okay, well, are there any TSP tors of size 1, size 2, size 3, size 4, size 5, all the way up. And you might ask, okay, well, how big, how much could the cost of the optimum TSP tor be? because you're going to have to go at least up to that before this algorithm would work. But you'll notice that if I do something like that, you'll notice that it'll actually depend on the actual values of these edge weights, because it'll depend on the maximum value probably of at least one of these edges, or the minimum. It's either way, it's the cost of the minimum TSP TOR, which is dependent on the edge weights. So normally you would not want to do that. If you were to do something like that, you would probably want to be a little bit more particular with the input size. However, there's better ways of handling this. You could use something like binary search. But either way, that's not going to help you very much, as we're going to see later on in this class. This is probably one of the tougher optimization problems to approximate over. So right now we're just considering the decision problem here. Now, that brings me to my next point. So my next point is I'm going to talk about two particular complexity classes. So there's going to be two complexity classes I'm going to be interested in this class primarily. Maybe more if we get into more details. So I'll say two complexity classes of interest. So the first one is the complexity class P. You might know this. This is the set of all decision problems that can be solved. You're going to guess it because it's a P there. Can be solved in, and I'll put in parentheses, deterministic polynomial time. So the P's makes this really intuitive. Just think P polynomial. Now this is where usually people get things wrong really fast. They see NP like this, they think not polynomial. Now intuitively you'll run into the case that maybe that might be what you might think, but that's not really what it means. The NP stands for non-deterministic polynomial time. So I'm going to give you two different ways of interpreting NP. I'm going to use one of them. It's a little bit more algorithmic friendly. The set of all decision problems. It's the set of all decision problems that can be verified. In polynomial time. So I'll just say polytime as an abbreviation. Whenever I say polynomial time, if I write polytime, that's what you should interpret it as. So equivalently, so that's one interpretation of it, but it's equivalent to the more traditional one. Equivalently, it is the set of all decision problems that can be solved in non-deterministic polynomial time. So that's where the N in NP comes from. Okay. So those are our two definitions. Now P is very intuitive and simple. And oftentimes you'll broadly see that P is just not even classified just as decision problems. I'm going to be a little bit more particular in this course. So when I say P, I think decision problems. But usually you can get a little bit away with just saying, okay, well, P just consists of all the problems we can solve in polynomial time. Good enough. But I'll try to avoid doing things like that. Okay. So I want to talk more about NP and how we're going to use it. So I got to first ask you a question. What does verified mean? Because you'll see my definition, when I say verified, you might want to have a better idea of what that means. Okay, so what is this going to be? So I gotta be very careful here when I describe things because this is a fairly complicated topic if you haven't learned this before. So when I talk about verify, I want to imagine I had one of my friends come over and I was working on one of my problems and I'm saying, hey look, I'm working away on this, and your friend comes over and just interrupts you and says, hey guy, I got a solution to your problem. And they give you a problem instance and they believe it to be a solution, or in our case, a yes answer for a problem instance. So if they give me something that looks like what we'll call a proof that is short, which we will talk about and say it's polynomial in length, it is short and easy for me to check. That's going to be what we're going to mean by verified. So let me write down a little bit more here. Hopefully I'll give you some intuition for this. Okay. So it means we are given a quotation marks short and easy to check proof. And I'll use proof in quotation marks. I mean this in the most symbolic way possible. And when I'm trying to assert that it is in fact a yes answer, I'll call this a certificate. A certificate that the answer is yes. So imagine your friend came over and they just tried to guess the answer to your problem. So, for example, if I had the traveling salesman problem, they might try to take a guess of what a TSP tour would be that would answer yes. So there's going to be kind of two phases to this idea. You can think of this as, I want you to think that somebody did a guess, and your job is to check it. So the job of our verification is to perform the check. So this proof, you might ask, okay, well this idea is very abstract to me. What do you mean by proof? So usually it's a little bit easier to explain as just with some examples, because the proof is something that's a little bit free. You can decide on what the certificate will look like, but it can't be too long. It must be polynomial in the input size, for example. So just like when we talk about polynomial time, you'll see that proofs have to follow very similar rules. So here's some examples. So if I give you the decision version, so I give you decision MST, so like our minimum spanning tree version of the decision variant of minimum spanning tree, you assume that your friend gave you a spanning tree. Or if you're thinking about decision TSP, which we're going to consider, decision TSP, you just think it's a cycle. So if I gave you one of these, your job is to determine if it's correct that is in fact a spanning tree and it has a cost at most k. So that's all your job is to do. Decision TSP, you give me a cycle, so your friend writes down a cycle, your job is to check if they've in fact given you a TSP tour with such that the total cost is at most k. So that's your job. So you want to think about it as, I'm looking to verify that it's a yes answer. So somebody gives me something and I want to check it against the input just to see if they're right. So I'm going to try to go a little bit faster here because there's two things I want to still show you. So first, I need to define a little bit more formally what I mean by verified, because I'm giving you some of this intuition. I mean, I think it's not too bad as long as you just don't let too many extra things get into play. But I'll give you a formal definition because I like to do that sometimes. So here's what the definition of a polynomial-time a polynomial time verification algorithm. So polynomial time verification algorithm. So I'm like, for a decision problem, pi, it is an algorithm. I'm going to give the algorithm a name. I'll call it A. And it's going to have two parameters to it. I'll just put dots there as placeholders. And two polynomials. P1 and P2. So remember, these could be any polynomials. As long as they're just two fixed polynomials, I don't care what they look like as long as they're polynomials. P1 and P2, such that for every yes instance, x in pi, there exists a proof y with where the length of y, the input size of y, is at most polynomial sub 1 of the size of x. So the way you could say this is the input size of the proof, or the length of the proof, is at least the first polynomial in the input size of the input instance. So x. So such that AXY returns yes. So remember, I want you to notice that it says there exists here. So I get to pick what the proof looks like, because it's just it just has to exist. You're going to notice an asymmetry in this definition right here. For every no instance, x in pi, for all proofs y, so remember I'm just assuming the proof that you gave me, for all proofs y, so all possible proofs of that kind of encoding, where the length of y is at least the polynomial 1 of the length of x, just like we had before, AXY returns no. And this is the last part of the definition. And I might need a few more minutes, so please excuse me in this, because I want to try to get to this one proof. So I want to show you one proof at least before we stop for today. No, and lastly, the time complexity of AXY. Now remember, x is our instance, y is the proof. So remember, I get to determine what the certificate looks like. But remember, the certificate can't be too long. So such that the time complexity of AXY is the big O of another polynomial, p sub 2 x y. So this second polynomial must be a polynomial in the input and the proof. Okay, so as long as our algorithm runs in polynomial time, we're okay. Okay. So I just want to say, so this is outside the definition. So if a decision problem pi has such an algorithm, pi is in NP. Now, this is the formal definition of the polynomial time verification algorithm, but I worth and stress, take my intuitive explanation before it if this is really confusing to you. Now, I must stress something that a common mistake that students tend to make involving NP and this verification process. This is just an important note. So I'm going to go a little bit longer. I apologize for that. But I really want to make sure I cover this one proof so that we can actually start getting into material next lecture. Okay. So we just need to, we need to verify y is correct or incorrect. Correct or incorrect for x. Assuming it is a yes instance. Now, this is the big bullet, is I need to say we do not need to show that x is a no instance. That's the very important point I want to make involving this process. So remember, all I'm doing is imagine somebody gives you a potential solution. You just want to check if that proof, or in our case, you can think of it as a certificate, is in fact what they claim it is. Is it a traveling salesman problem? Is it a TSP tour of a size at most k? Sorry, total cost at most k. It's not your job to present that there is no such TSP tour. That's not your job. I apologize for going a little longer here, but I want to give you one more thing today. So I want to prove that our decision version of TSP is an NP. So I want to show you us using this. So the claim is that decision TSP is in NP. So our job is to give a verification algorithm that runs in polynomial time, right? So we're going to give a proof. So normally when it comes to this, I recommend first stating what you're trying to prove or what you're going to do. I always like to think of it like a game plan. So to prove our problem, is in NP, we present a polynomial time verification algorithm given, now I'm going to specify what the certificate is, given a cycle C to be checked. Now, I think in cases like this, it's not too hard to really see that the certificate is in fact going to be, its length is polynomial in the input size of the input instance. Why? Because this is just going to be a list of vertices. So I just specified the cycle. But that's good. That's perfectly fine, right? We're not doing anything out of the bounds of polynomial time here. Remember, you get to select what the certificate is. However, it has to be something reasonable. It has to be within polynomial time. But remember, I recommend just picking something that seems obvious. So like in TSP, okay, just pick a cycle. If it's maybe a spanning tree or something involving trees, probably some sort of tree that where you have to check things about the tree. If it involves a scheduling, maybe something involving the numbers. I have to check, so I give you a schedule, for example, in a scheduling problem. So just give me the schedule, I'll check it. So this should be, don't let that formal definition scare you. Just think of the intuitive way I described it. So I have a cycle. Now all I have to do is just give you the algorithm, and it's really simple. The algorithm evaluates if all the vertices in C are distinct, and that the sum of the edge weights of edges in C does not exceed K. Now, before I get too ahead of myself, why is this okay? Why is this fine? I'm just checking if all the vertices in C are distinct. So now keep in mind, when I'm encoding this cycle, I'm not going to include the front and the end of the cycle because they're just repeating, so I'm just going to assume only one endpoint. So I just need to check if they're distinct. Remember, I assumed that the input was a complete graph, so there's going to definitely be some Hamiltonian cycle, so I don't have to worry about anything strange here. There's always going to be a Hamiltonian cycle in such a graph. So as long as I just check if all the vertices are distinct, we're okay. If you didn't have this assumption, you probably have to do something like a depth first search or something, just to verify the cycle. Which you can do in linear time still. And we just got to check if our TSP tour is at most K, right? As long as we check these two things, what should we do? If true, then return yes. Now what do we do if any one of these two is violated? That means that we do not have, in fact, a TSP tour of cost at most K, right? It's either not a TSP tour or it exceeds K. Otherwise, actually, we'll not make that a semicolon. Let's just make it a comma. Otherwise, when false, return no. Now, I need to make sure I state this somewhere in my proof. This algorithm is really straightforward, but if you're working on a more complicated algorithm, you might have to actually pull out the time complexity analysis. This one, I'm just going to say, this algorithm takes polynomial time. And we're done. You could finish this off with a therefore. We presented a polynomial time verification algorithm, but for the sake of time, I'm just going to finish it here. I'm going to mark that we've completed and ended our proof. Okay? So I wanna say one last thing. I know I'm quite a bit over, but I'm just going to finish up with one kind of interesting question. And this will kind of wrap things up nicely for us so we can just start off things next day. I'm losing my board. Let's go get back. There we go. Okay. So I have two questions for you. Just based on the kind of the intuition we've been playing around here, I have one question. So question number one. Question number 1. That's a horrible E. Let's fix that. Question number 1. Now remember, I described the P and NP as computational complexity classes or sets of decision problems. We should ask a couple questions here. Do we know if P is a subset of NP? Let's think about this for one moment. Is P a subset of NP? Well, the great thing is the proof for this is really easy. The answer is, in fact, yes. There's 2 ways you can approach this. The theory of computation way is you can say, okay, well, every deterministic Turing machine is, in fact, a non-deterministic Turing machine. It's a special case as well. The other way, and this is the way I find more intuitive, is using our definition of a polynomial time verification algorithm. Remember, it has 2 parameters, the input and this proof. Here's how the proof goes. It's really simple. Just ignore the proof, solve the input. If it's in P, there is a polynomial time algorithm. Just use that and say yes or no. Just like our 2 examples where we had polynomial time algorithms. It works just like that. That's why I wanted to show you those couple of examples. Because the proof looks just like that. It's just, instead of it being just, oh, well, it's just for this specific problem. Remember, P by definition has a polynomial. Any problem here has a polynomial time algorithm. Now, the other question, this is the one that's very interesting. Question number 2. Is NP a subset of P? Now, some of you might be watching this and saying, Dan, why would you have something silly? It's obvious the answer is no. Now, I don't know this, because there does not exist a formal proof for this. The answer is I don't know, but it's probably, we don't know. However, you're going to find in this course that we're going to kind of build on the intuition that the answer to this is probably going to be no, but we don't know. At least most theoreticians believe the answer to this question is no, but they don't have a mathematical proof saying so. So you're going to find that a lot of the problems we're going to run into will fill in a lot of intuition of why a lot of theoreticians tend to think the answer is no. Not every reason, but some of them. We're going to explore some problems where it's not quite clear how you could possibly do better. Anyways, so if you're wondering what this is just simply the P versus NP problem. This is broadly regarded as the most important open problem in all of computer science today. And just in this lecture, we've kind of set up everything to talk about it. So, that being said, we want to know more about these, and just two things I want to say. So we want to know if P is equal to NP or P is not equal to NP. If the answer is yes here, then P is equal to NP. If the answer is no here, then P is not equal to NP. So inside NP, there is a class of problems called NP complete. Called NP complete. Consider the hardest, and I'm going to use hardest in quotation marks. Don't get any weird ideas when I put in quotation marks. I mean hardest in like, oh, difficult, really hard. Not any other ways. Don't use your imagination on that. Okay, so the hardest problems in NP. In fact, any problem in NP can be reduced to these problems So worth noting here, when I say reduced, I mean a polynomial time reduction. We're going to see some examples of these in this course. You may have encountered these in the past. But the point I'm getting at is that any problem in NP can be reduced. So I can take any NP problem, turn it into an NP complete problem. If I could solve an NP complete problem, I could solve all the ones in NP. Actually, I should be a bit more precise with that. If I have an NP complete problem, and I can show you there's a polynomial time algorithm, what I could do is I could transform any problem in NP into that NP complete problem, run the polynomial time algorithm on it, and I could solve those in polynomial time, right? So that's what makes it very fascinating. So if that were to happen with these NP complete problems, then P would be equal to NP. But this is just the one point here. The main thing I want to say is the following. And this is where I'm going to stop for today. Is on the notion of NP hard. Because that's the one we're really wanting to talk about in this class. Okay. NP hard problems are similar to NP complete problems, but need not be in NP. I'll get a little excited there. But need not be in NP. So in fact, if you were to look up the formal definition of NP hard, that's mainly this part right here, the second part here. That any problem can be from NP can be reduced to these problems. That's the part that really makes NP hardness. The part being in NP is what makes it NP complete, because that has to be a decision problem. So that's what I'm saying, is that NP hard problems don't have to be decision problems. So what I mean by this is that if I give you an NP hard problem, the types that we're going to look at optimization problems, what you could do is you could transform these into NP complete problems by simply doing what we did today. Some reason I can't write complete. Let's do that again. NP complete. What we could do is we could take an NP hard optimization problem and transform it into an NP complete problem by turning it into a decision problem. That's the big point. That's the big thing here I want to take back on. So if I give you any NP hard problem that's an optimization problem, you could phrase it in terms of a question, just like what we did with the minimum spanning tree, just like what we talked about the traveling salesman problem, and you could get an NP complete problem. That's the big thing I want to say. So one other point before I stop. If you're looking for another way of thinking of NP hard, all you have to do is you take a problem and you just say, okay, well, if I know a problem is NP complete and I want to show it's NP hard, all you have to do is, if you want to reduce from an NP complete problem, you perform this reduction. But what you would do is you would assume that you could solve the NP complete problem in one step. This is the so-called Oracle approach to proving NP hardness. If you're curious more about this, you're more than welcome to ask me, or I can even put up an example if you find this curious. But beyond that, we'll see examples of reduction, so don't worry if that at that last step here was a little bit strange, or you just weren't sure what I meant by this. We'll see examples of this later on. So anyways, we'll stop right here, and I apologize for taking your extra time here. So hopefully that is okay. Next day we're going to talk about what an optimization problem is, and we're actually going to start talking about approximation algorithms. So I'll see you there. Have yourself a beautiful day.